am a little bit picky about my sinusoids. I like them to be pretty, and so I want to make sure you can graph a sinusoid well. All right, so let's go here. First of all, before you do that, let's talk period. What's the period of this here first graph? How do you find the period? All right, so let's go here. For sine or cosine, it's normally 2 pi for a full period. But if there's a factor with the x, then it's stretched or squished horizontally in an inverse kind of way. So for example, if you want the period of a sine curve or a cosine curve, you'll take 2 pi and divide it by the coefficient. So in this case, the period is, speak, 2 pi over 5. Wonderful. In this case, the period is 2 pi divided by what? 3 halves, and when you multiply that, what do you get? 4 pi over 3. Wait. Now for tangent, the normal period, and cotangent, the normal period in tangent is not 2 pi, it's pi. It goes through a 4th cycle. And then likewise, you're going to change the coefficient if there's a stretch factor. So in tangent or cotangent, you take the normal period of pi divided by the coefficient. And so this wave would have a period of pi over 3. Do the other two real quick, and we will move on. Okay. So the next two are kind of funky in that they've got pi in them. That's great, actually. In real life, that's typically how you would model, because in normal periodic movement of life, you don't really have 12 pi months in a year. You have 12. And so you'll often, in real life modeling, see a pi in there because it cancels the pi out. What is the period of the fourth? And the last one? 4. Okay? So if I were to model something periodic, like the angle of the sun over the course of the day, or the temperature over the course of 24 hours, or how many ice cream sales over the course of a year, those are all periodic. They go up and they go down. They go up and they go down. You talk the height on a Ferris wheel, periodic. There's so many uses to this. It's amazing. Now then, let's talk about graphing the sinusoid. I wish I would have had the time to me do one and then you do one, but you'll do one on the homework. I slightly changed these notes, so we're going to go with what you have, okay? You with me? So the first thing is, I know it says factor first, but let's start with the shape. What does a positive cosine look like? Peak to peak, yeah? What does negative cosine look like? Man to man. What does positive sine look like? Starting at the middle and up. And negative sine? Middle and heading down. Okay, so this will be a peak-to-peak wave, yay? All right, cool. Let's go on to the next thing. It must be factored. In this case, it is factored. But if it had been 2x minus pi over 3, the first thing you would do is factor, because otherwise you will make a mistake with the shift. So factor first. In this case, I'm giving you factor form. Let's start with the starting point. This guy shifted it horizontally. How? Right, left, up, or down? Right, you have to be a knucklehead to say up. I just said horizontally. So right, pi over 3. So the starting point, quote unquote, is pi over 3. What's the period? You just did this. Come on. Pi, okay. So what would the end of a one wavelength be? If it started at pi over 3, did pi for a whole period, where would first wave end? 4 pi over 3, beautiful. All right, now here's where any teacher with salt would want you to go exact. What does it say next? Interval or quarter wave, something like that? On the steps on the right, what does it say? 1/4 wave. Okay, so all sinusoids should show 5 points per wave. the start, the quarter, the half, the three-quarter, the end. That's 5 points per wave to do any good wave, all right? It will not do to say, all I need is the starting point, the ending point, and who gives a rip what's inside. I give a rip what's inside, okay? So you must have 5 points shown well, and to do that, you need to know where the quarter waves are. Now, if a full period is pi, then what's a quarter period? Pi over 4. Beautiful. Now, that's going to be great, but when you go to choose a scale, you want to be able to locate your starting point, but also be able to go a quarter wave to the next point. So it helps to have a common denominator between these two so you can find them both. So what's the common denominator between pi over 3, the starting point, and pi over 4, the movements? 12, pi over 12, all right? So our starting point is going to be 4 pi over 12. The ending point is how many pi over 12s? 16 pi over 12s. And each quarter wave is how many pi over 12s? 3 pi over 12s. All right, now make a pi over 12 scale, and I'm just going to show one scale mark. I think it gets a little busy otherwise, so I'm just going to show one, all right? The vertical part usually goes well. What's the 3 do to the graph? Shifts it up. And so normally a sinusoid centered at the axis, so you could say now it's centered at 3. So that's the center line, it's 3. What does the 4 do? Speak louder. Changes the amplitude, or it's a vertical stretch, whichever you like. So what's the maximum? 7. And what's the minimum? -1. It's in there, yeah? The range is between -1 and 7. Okay, so let's find that starting point. The starting point is 1, 2, 3, 4 pi over 12s. And is that starting point a minimum, a middle, or a max? Based on positive cosine shape. It's a max. So we should have a max at 4 pi over 12. 1, 2, 3, 4, a max. Now, the second point is a quarter wave away. So how many pi over 12s do I go to the next point? 3. So I'm going to go 1, 2, 3 over. And will I be at the top, the middle, or the bottom? Middle. And I'm going to go 1, 2, 3 over. And where will I be then? The bottom. Might as well go back from that starting point. Going from that max, let's go backwards. 1, 2, 3. And that'll put me at the middle, yeah? Count more. 1, 2, 3 boxes, min. 1, 2, 3 boxes, middle. 1, 2, 3 boxes, max. And so on. So, if your wave is accurate, and yours is, I'm sure it's beautiful now, it should look like that. Give me the location of 2 maximums, please. Give me the x where there are 2 maximums. 2 x's where there is a maximum. Give me one. Talk to me, people. There is a maximum at 4 pi over 12. What else? 8, -8 pi over 12 is 8. Okay. That's how I grade it. I'd say, all right, if this is graph well, it should be max here, max there, min here, min there. It should be accurate at all quarter point waves. Are you with me? Okay. We'll practice that tonight, and I want it done well. Next thing, conic sections. There are 4 types of conic section: circle, parabola, ellipse, and hyperbola. And although you might think, math people need to get a life, these come from taking this picture and slicing it lots of ways. If you slice it this way and look at the cross section, what is it? Circle. If you slice it this way and look at the cross section, it's at an angle, and now it's an ellipse. I need to draw another picture. If you slice it this way And what's this cross section? That's a parabola. And then you slice it this way. What's that? Okay, then you get a hyperbola. Now, again, like I said, why would you want to slice up a bunch of cones? Who cares? Well, all these have huge relations to real life phenomena. I mean, hyperbolas, when you talk planetary movement of something that gets slingshotted around a gravitational pull, it's a hyperbola. Parabolas, any projectile motion problem due to gravity is a parabola. Ellipses, gosh, anything, there's a kidney machine that hits kidney stones based on the idea of an ellipse and foci. There's just so many points to this, okay? So it's not, who cares? They have real applications. Circles, obviously, is huge. General form for all is this. All conic sections use that same general equation, and based on A, B, C, D, E, and F, you get different types of graph and their signs. B, we don't go there at this school, and it's probably not even taught anywhere except until you get to Calc 3. But that is the worst. It is disaster. This causes rotation of axis. So instead of an ellipse going this way or this way, it'll go this way. Or a parabola will go this way. It is a mess, and it's the worst. So you probably won't go to that B term. We're going to go pretty straightforward, all right? If you have this equation and one of the squares is missing, so you only, for example, have x squared, then what kind of graph, circle, parabola, ellipse, or hyperbola would that be? Parabola. If squares have opposite signs, like x squared minus y squared, what's that? That's a hyperbola. You have been taught very well, I must say. If the squares have the same sign, but the coefficients are different, ellipse. Why? What does the coefficient do to a graph? It stretches it. And if those are different, then the stretches are different. One will get stretched more than the other, you get an ellipse, right? And if they are the same and same sign, circle. Okay, so would you give those bad boys a look, and you could just put down the letter of which one you feel those are. That should be sufficient. Ready? Listos? Let's talk some participation here. Sam, what'd you say for the first one, man? Circle, well done. Maggie, what'd you say for the second one? Hyperbola, I agree. Kelsey, what'd you say for the third one? It is in the lips. Abby, what'd you say for the fourth one? Parabola, yes. That's a sideways opening parabola, yeah? What about Corey? What's the fifth one? Say it again? Oh, my bad. Oh, I'm sorry. Now I understand. I didn't actually look up. Harrison, what do you say for the fifth one? Parabola, I agree. What form could you easiest, you can graph from standard form or factored form. Which would be easiest to go to there? Factored form. And what does factored form tell you for a graph? The x-intercepts are the zeros, yeah? Although completing the square wouldn't be bad either. What about that last one, Taya? Again? Hyperbola. Wait. Sorry, I'm real deaf, people. Now, many of these graphs fail the vertical line test. I think you'll agree. Do you remember the old vertical line test that says if it's really a function, then when you put in an x, you should get 1 point out, not 2. It's not. It should be. When you put in a 2, you can get a 3 or an 8. That's not a function. that would mean that graphically speaking, if you put in an x, you got two different y's, those are not functions. In calculus, we often only want to work with functions because derivatives are a little harder to take if it's not a function, and areas are a little harder to find. All these things you'll see. But sometimes you'll see those graphs look a little different equation-wise, okay? So bear with me here. If I asked you to graph this, you might think, well, I don't know what that is. Is it a square root graph? Is it a parabola? The answer is neither. It's neither one of those. That's silly. That's not it. Instead, think this. Could you not square both sides? I'm going to replace it with y instead, right? So if you square both sides, then isn't it y squared equals 36 minus x squared? If you then move the x squared over, you get x squared plus y squared equals 36. Now, what does that feel like? A circle, but is it a whole circle? No. If I went backwards and solved this for y going this way, when I square root, what do? I get plus or minus, but there's only plus here. So instead of the whole circle being there with a radius of 6, y is only positive, so it's only that piece. And the bottom never happened. You follow? Okay, try the others then. My goal is for you to play with the equation a little to see what conic section it is, and then decide, is it top half, bottom half? Did I run out of copies for those? Were there enough copies of that? Yeah, Honor Society. We good? Okay. I thought I would run out of copies. The little one. I'll do that later in the third, okay? Is that ready? Okay. You're just finishing up. Jim, the second one, what figure, what half? Hyperbola and top half or bottom half? Okay. So, was it sideways opening or vertically opening? This one's y squared minus x squared. So does that mean it opens opening up and opening down, or opening right, opening left? Jim? Good. Up and down. And so it would just be that graph. Yeah? Can we pause a second to think? Are you with me here? Check this out, my friends. What do you know about what's this called again? Hyperbola. What does it do at the end? It starts to follow asymptotes. Okay, let's talk calculus, shall we? In terms of end behavior, as x gets infinitely large, which is the dominant term? X squared or 36? X squared. So as x gets infinitely large, this means less and less, and it starts to behave more like the square root of x squared, which is x. By end behavior, it starts to approach more of a line. And plus or minus, it would be negative. So hyperbolas follow asymptotes, not because somebody said, hey, this will look cool. It's because there is a reason, end behavior. All right, this next one. Steph, what did you say? What kind of figure, what half? Top or bottom? Ellipse, top half. Do we all agree? Or top half or bottom half? Bottom half, okay. And are we all cool? It feels like that's right. What about the next one, Martin?
I said it was a triangle up.
It's opening up and down or sideways? I agree. And top half, bottom half, or both halves? Both halves, yeah. Because of the plus or minus, it's both halves, so that's true. What about g of x? Lexi? Do I agree with you? And I do. Is it a sideways opening or vertically opening one? It is sideways. Is it the top half or the bottom half? Is the top half y is positive, and so it would look like this. Yeah? Let's talk domain here and why this makes sense. In order to keep from getting a negative in the root, what must x be? On the positive side, it has to be greater than 5. And on the negative side, it would have to be less than negative 5. So that also makes a good deal of sense. And the last one, Monica, what kind of graph? Hyperbola, and what kind of, I agree with that. Y squared. I think circle. Do you agree? Because that's negative goes away with squaring when you square the whole side. So circle, bottom half or top half? Because y is negative. Yeah. Okay, cool. That I don't know if you've done, but it's important for calculus, so here we go. Next thing, conic sections in your calculator. Would you get out your calculator, please? If you need one, go ahead and borrow one. You'll need a graphing calculator. And here we go. I think you might have to call TI and ask them for a battery. We play it around with the battery's not hard to replace. It's not very much, but that's what you'll have to do. Okay, so here we go. I can't remember what I asked you to do. We're going to solve that system graphically, okay? Now, if you have, does anybody have an 83 or 84? Okay, not in this class. That's great. All right, so here we go. If I want to put this in, then go to the graphing menu, and the great thing is that one of those is a function. Which is a function? Y equals x plus 3. So when you go there, you can put in x plus 3, and you're getting a line, which is obvious. Are you with me? Now, for graphing the conic, you're going to need to do things a little differently. That is not a function. It is two functions. Now, we could do it that two ways. We could actually solve for y and make it a function, which we're going to do in a minute. But your calculator, if your Inspire is updated, also can graph it the way it is. So you could either graph, there's a conic here, you could graph one of these, general conic. I gotta be honest with you, I just always go to the relation idea. If you want to play around with the conic, then you please do that, but I'm going to go to the relation. Are you with me? Okay, now when you say relation, it just means x and y are related in an equation. It doesn't have to be a function. So if you type in the equation the way it is, x squared minus y squared, x squared minus y squared, what did it say after that? Plus 2x plus 2x minus 4y minus 9, and equals 0. Equals is up below the control button. If you hit enter, you got your graph. You cool? Does your graph look something like that? Okay. Now we want to find the solution to a system. When you solve a system, what are you doing? Defining intersection points. So we go to analyze graph. And we're going to hit intersection. Now it needs to be told where to look. So we're going to tap, we're going to, basically, it's you make a box around where you want it to look, and I want it to look here, yeah? So I'm going to tap there, and then tap a second corner there, and my calculator's, is it that clean, or is it rounding to 2? Is yours giving more, or is that what yours is giving? That? All right, we definitely want 3 more decimals if they were there, but it's cool. All right, so we get intersection points, and again, you're just kind of making a box around the where you want it to look. So if you didn't get that, I'll come around in a second, but would you say the solution is negative 3.75, negative 0.7? You tracking? Okay, so if you have an updated Inspire, I don't know if you need to, if you feel the need to write those instructions down, great. You might just write yourself a note that says, in graph entry, use relation mode for that non-function. Okay. All right. Now, are you with me? Okay. Now, it is often the case, however, especially for calculus, that you want it to be a function. There are some things that the calculator still can't do in a relation mode, calculus-wise. So we are going to sometimes have to go through the rigmarole of solving for y. Let's start here. X equals y squared is not a function. Why not? Yeah, it fails the vertical line test. When you put in an x, you get 2 y's, so on. So fails. Let's just say fails the vertical line test. All right. Now, if I wanted to graph that in function mode, then I would have to solve for y. When I solve for y, I think you'll agree I get plus or minus the square root of x. So you would have to, in function mode, you would actually have to graph that in 2 functions. f1 would be the positive root x, and f2 would be the negative of root x, and then you've got your sideways opening parabola and function. It's kind of a word. You with me? All right, now that wasn't too bad, but the real drag is when you have to do something uglier, like put that into your calculator without relation mode. So I need to write that down, x squared minus y squared, x squared minus y squared plus 2x minus 4y minus 9 equals 0. Is that correct? All right. Now our goal is to solve this for y. So towards that end, what should we do first? Yeah, y is to one side. I'm going to move them to the right side so the y squared is positive. You want a positive y squared. So when you do that, you have y squared plus 4y on one side and x squared plus 2x minus 9 on the other, unless I made a mistake. Do we all agree? All right. Now the problem, the age-old problem that took hundreds of years to deal with is, how do I solve for y when I have 2 different powers? You say, well, shoot, that's a square, and I would square root, but that makes this a mess, and so it's a big mess. What's the way around it? 3 words. Complete the square, okay? So what goes here? When you complete the square, you look at this guy's coefficient, and you take half of it and square it. So what goes there? So I need a positive 4. Whatever you do to one side, though, you must do to the other. So I'm going to complete the square. On the left-hand side, I'll total that. Actually, what's the left-hand side now? X squared plus 2x minus 5. And on the right-hand side, the whole purpose of that was to make a perfect square. What is that, the perfect square? y plus 2. The reason is now you don't have a mixture of powers. It's all one big square, so we can square root. Y plus 2 is, when I square root it, plus or minus root x squared plus 2x minus 5. So at the end of the day, y is, move the 2 over, negative 2 plus or minus the square root of x squared plus 2x minus 5. Now I went kind of fast. Are you with me? Let's verify we did that well, shall we? So would you go to Document and scroll down to Clear Scratchpad? And then go back to the graphing menu, and we're going to graph that hyperbola with our solutions to see if we did it right. It should look like the hyperbola we just had, yeah? So in F1, let's go the negative 2 plus the square root. What is it, x squared plus 2x? Oh, I can't remember. Plus 2x? Minus 4x? Minus 4x? Minus 4x. Nope, it's plus 2x, isn't it? Are you with me here? Negative 2 plus square root of x squared plus 2x minus 5, yeah? And that gives me the top half of the hyperbola. Are we cool? How do I get the bottom half? Minus, is there a way to cut and paste that so I don't have to retype it? Does anybody know that? What is it? Oh, someday I'm going to have to figure that out. All right, so negative 2 minus square root x squared plus 2x minus 5, cha-cha-cha. Boom. Okay, so all together we get that same hyperbola, and although it was more work, we can do a lot of calculus with that in functional. Are you with me? Okay, so is that the end of the notes? Please tell me yes. Boom, here we go. All right, so go to green. This is the greatest shortcut in all of mathematics. If I made you do x to the 100th first, then you would see just how awesome it is. But here we go. There is a shortcut. There are many shortcuts for finding derivatives. If you ask a student in BC or something, hey, take the derivative of this, they wouldn't bust out the definition of derivative unless they had to, unless the teacher made them do it. It's the concept, and that's why it's taught first, but there are quicker ways to find the derivative, and you'll see it's super duper easy. Here we go. Would you take the derivative by the first definition, and I'm going to use h rather than delta x, but you could use delta x if you like. You should know deep down all three definitions of the derivative by the test on Friday, and be able to find the derivative by the definition. Is that going well? Are you succeeding there? Okay. Would you then do that, please, for x squared? Did you get 2x to the first, or still working? Still working. Speed it up, people. I got places to be. We good? Okay. All right. I'll come back to that binomial expansion idea in a second. Let's go to the derivative of x cubed, please. Crank that out. You remember what the binomial expansion of x cubed is? x cubed plus 3x squared h plus 3x h squared plus h cubed. We might need that in a minute. I'm going way too fast, so just do your thing. And your goal is to look for trends along the way. You said all great steps forward by mankind came with the frustrated statement, there's got to be a better way, there's got to be a better way. So after doing some of these, looking for trends and saying, is there a better way, is there a better way? What's happening each time? That's what I want you to focus on, all right? Eventually, on the second one, the derivative of x cubed came out to be 3x squared. Is that how that, is that cool? Okay, I know it's tedium, but let's do one more, and then I'll pay off. The expansion of x plus h to the fourth is x to the fourth plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the fourth. X to the fourth plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the fourth. Will you win? Okay. Now looking for trends here, each time, every one of these times, the first term subtracted away, yeah? You agree? And then as far as the h's, the second term had a single h and the rest of them had multiple h's. So that after dividing out common factor h, the first term had no h's, but all the other ones following did still have h's. H squared plus h cubed. So that when it was all said and done, only the second term was left standing, and your derivative came just from the second term. And we'll talk about the numbers you see. Obviously, they're changing each time. You tracking? So if we were to do this generally, looking for a general formula, a general expansion of this starts with x to what power? When you expand x plus h to the n, it starts with x to the n. What about the first coefficient? If you look back here, when you do a cube, the second term's coefficient is 3. When you do a fourth, the second term's coefficient is 4. So when you do the nth, the second term's coefficient is n. X to the what? N minus 1, because it decreases each time, and h increases each time. Okay, now this guy has a coefficient rule. We could use Pascal's triangle or combinations to get it, but it's not an issue for calculus, because isn't this guy going to drop out anyway? Because it continues to have h's even after the definition of the derivative. So don't sweat the coefficient there. But what is the last term, just for the kicks of it? It ends at h to the n. All right. So if I wanted to do a general rule for the derivative of x to any power, and it doesn't even have to be a whole number, then it would look something like this. The limit as h goes to 0 of x plus h to the n minus n, x to the n over h, okay? And then each time we expanded the binomial, and that's what we have over here on the right. It's x to the n plus n x to the n minus 1 h plus something x to the n minus 2 h squared. Continue on through h to the n, okay? After that we've done expanding, we still have to subtract x to the n and divide by h, okay? Now each time, remind me again what happened? What's the first thing that happened? X to the n subtracts away every time. And then everything else has an h. When you divide out that h, the second term, the n h rather drops away, and what's left? Nx to the n minus 1, and the other terms all have an h in them. H squared, h cubed. So at the end of the day then, when the h terms drop away when you do the limit, what's left standing? Nx to the n minus 1. So it feels like the quick way to take the derivative of x to the n is the exponent comes down and becomes the coefficient, and the exponent drops by 1. The original exponent comes down, drop the exponent by 1. All right, so now then, actually, let's go back then and make sure that made sense. When we took the derivative of x squared, wouldn't that be the original exponent comes down, reduce the exponent by 1, 2x to the first. Isn't that what we got below? Okay. When we took the derivative of x cubed, the original exponent comes down, drop the exponent by 1, 3x squared. We can see that we get exactly what we expected each time, so it feels like it's working. All right, so that said then, be careful here. I'm talking about notation. First day, students will often say, oh, so this is 7x to the 6th. What's wrong with what I just did? Yeah, okay, it's not that you didn't do the derivative right, so your notation is garbage, because that's not the function you just found. What is it? It's the derivative, and your notation should indicate such. You should say, in a second line, f prime is 7x to the 6th. Oh, it's over here. My bad. Sorry, I should read my own notes. Woo. Okay, now, the cool thing is that helps, or that works even on roots. I would strongly recommend that if you're given a root or a fraction as an exponent, take a rewrite step before the derivative. So if you rewrite this as an exponent, what's the square root the same as exponent? Okay, now I didn't take the derivative. I just rewrote it algebra style. That was an algebra step there. When I go to take the derivative, now I can use the power rule. So what two steps to a derivative? First, the exponent comes down, and you drop the exponent by 1. So maybe 1/2, not maybe, 1/2 x to the negative half, okay? Or if you like, how could that be rewritten with roots? 1 over 2 root x, yeah? Try the next one then, using that idea. Write a cleanup step, then take the derivative by the power rule, and along the way, be careful or be grateful that you're not having to do the definition of derivative to do it. What is that as an exponent? So it's negative 1/3 to start with. So if I do the power rule on that, what do I get? Without any cleanup step, just negative 1/3 x to the -4. There you go. Okay? Greatest shortcut now. All right, didn't get to that, so, shucks, that's not you, I think you turn that in. So, I will probably have to do some questions at lunch and post them on my website, or you can come in 7th period. You can come in 7th period now, yeah? If you can't come in 7th period because you have other classes, and besides my class apparently, what questions on 21/22 would you like me to put up? Did we talk about how the Saxon answers are on my website? We talked about that, right? Okay, so really, as far as answers, you should only be in the Zarkons, the ones that I replaced. But that said, you might still have questions. So shout out any questions you want me to post at lunch on 21/22. Unless you're coming in 7th hour, in which case I can do both of you there. Whatever. How are you doing that? I'm going to hand back these quizzes. They're pretty darn good. I'll tell you what, I'm just going to put my marker there, and if you want those questions done, write it down, and I'll, and I will put them off at mine. Your homework is due by the end of the day. I expect to be here till about 4:30 or so today. If you can't come in 7th, but you can't come in after school, by all means. Oh, I was really happy to put this right. Overall, it's actually nobody's probably everybody has to see it. Sorry, I'll do it at lunch. Actually, maybe I can do it right now. Have a great day. Okay. There you go.
Starting the year off strong.
It's fine. Don't worry about your grade. Worry about the calculus. Have a great day. Thank you.